All right, so today will be the last class. The agenda, I think I will go over one more example about the recursion on the array, and then I will assign some reading for you that will be required for your exam, which will be the last example for Tower of Hanoi. So that's quite an interesting puzzle for you to solve. So some of you may have already seen that in your previous math course, but now this time you do add Java into the context. So I think that'll be a nice addition to study for the example. And then we'll take a short break after all these, and then we'll wrap up the course. Actually, before the short break, we should wrap up the course, and then we'll talk about the exam. Okay, so today, we'll see how that goes, right? But we're still going to go over one more example just to make sure you have enough basis to really do some examples on your own on the recursion on the array. Okay, so for the recap, I just want to focus on maybe just this last concept that we spoke about last time. Okay, and for other things about how you can do the reverse palindrome and also the occurrences of, so those are the recursions on the string, you can definitely give it a try on your own as well. Okay, just we already talked about them thoroughly in the class. Okay, so we talk about this idea here. So let's say you want to call a recursion. You want to do recursion on an array right here. So the base cases will be pretty much like a string. You got array being empty, or the array has only one element, so depending on the length. So these are the base cases. And in the recursive cases, you want to call something that's strictly smaller. So the most naive way will be just to simply create some subarray that's strictly smaller. And we discussed that this is very inefficient. So basically, every time you want to make a new recursive call, you have to create a brand new array by using a for loop to copy over all the old contents. It's a very computationally expensive. That's not a way to go. But the idea about creating like a subarray is definitely something we want to go for, but we want a more efficient way to really do such recursion. So this is the final pattern that we're going to follow for all the recursion on the array. So the way to do it is you still got the array as the input over here. And then you specify two integers. So these two integers are going to specify a range about the indices you want to go through in the array. So for example, in the beginning, you may say from is the first index and 2 is the last index of the array. So that effectively means you want to look at the entire range of the array. That's how we start with. And when you want to make the very first recursive call, you still pass the same reference of the array, call by value. You're not really creating any new array. So that's really important. We're not wasting any memory to accommodate new array objects. Instead, we try to play with the indices that we are actually passing. We used to pass the first and last index, but now we're going to pass the second and the last index. You can see from +1 and also 2. So we are moving basically one element to the right about the range of indices we want to look at, right? So that's something we're going to trace together to see how exactly that will work. In general, you don't necessarily have to always say from +1 and without changing 2. You can be creative about exactly how you want to narrow down the range of the indices. So this pattern here just gives you some example about how you can use a call by value and also use two integers to tell the recursive call exactly which range it should really look at. All right, so that's something you want to make sure you grasp. That'll be something you have to, you can also expect maybe some questions on this in the exam. Any questions about this concept here? Very crucial. All right. All good? Okay. And then that'll be about a recap I want to do, but you guys will definitely have to still make sure you understand this concept over here. But let's do one example together. I think that'll be important. Okay. So the example will be, let me see. Oh, there's something I want to mention. Sorry, just before I move on to the contest for today. Don't forget to submit your Lab 5 by December 9th, but I would say the earlier the better. You definitely want to review other stuff as well. And I posted some survey, like a questionnaire on the e-class yesterday. So if you haven't really done so, you can just go there and indicate which day or which time you prefer. I'm going to schedule at least one review session, most likely one, right? I also got your other fellow students from other courses I need to look after, but at least one. Okay, so we can schedule some review session to answer your questions about the exam. Most likely next week, may not be this week. I think you guys may want to study a bit before you got questions. I will also post a PDF exam guide just to give you more details about the policy and also some example question as well. But I want to give you guys some warning, if you don't mind. the example questions are on the easier side. They're only meant to be as examples. You don't want to rely on the example question to study. All right? What you really want to do is to really go over all the materials we have taught in this course. I'll give you a little bit more tip, maybe when I talk about the exam information, maybe after the break. But my point is, example questions are great. They can give you some examples, but you don't really want to prioritize your study over the example question. You want to prioritize your study by going over all the materials. Okay, that's really the message I want to give to you. Okay. And for your programming test number 3, I'm still waiting for the result from the TA. They should be able to get back to me by hopefully end of this week, and then I will process the result very quickly. Early next week, I'll reach out to you about programming test 3. Okay, let's talk about the content for today. Okay, so let's just solve one array recursion question thoroughly, right? So all the recursions on the array problems will be kind of similar. You will just have to make sure you know how to play with the indices specifying the range. Okay, let's see what this one is. Okay, it's a typical one. So if you look at the slides, it's slide number 21. All right. Given an array, we want to see whether or not all the integers are positive. If all the integers are positive, we return true. If not the case that all the integers are positive, at least one not positive, in that case we should return false. All right, so that's what the method should do. The first base case, which will be the most important one, a little bit tricky one to really get right? You don't really want to memorize the result. This one here. If the input array, we only assume the input array is not null. We just don't want to get into any null pointer exception. Apart from that, you cannot make any assumption about the length of the array. The array may be empty. The array may be of length 1, length 2, length 3, etc. All right? So let's start with length 0. If I got an empty array, I'm asking, are all the numbers in the empty array positive? Should it be true or false? This might be something you maybe solved, maybe back in 1021, maybe, I'm guessing. If not, here's the occasion. All right, we can pause a little bit, because this one, I would say, arguably, this might be the trickiest one for this example. What should we return for this base case? If the array is empty, and should we say true, all the numbers are positive, or should we say false? It's not the case that all the numbers are positive.
I think we say true because when we're going to reduce the array, if the numbers previously were positive, then we don't want to return false after we...
I like your reasoning, actually. You're basically saying, what if I give you empty array directly? What you're saying is, if I got something that's not empty, eventually, yes, the range of indices will get to empty. In that case, that means all the previous ones are positive. Right? I like the reasoning, but not complete. What if I give you empty array directly? There's no previous, right? But true is the right result, I can tell you, right? Okay. All right, so let's now, for this one here, let me just give you a little bit of background over here. This might be something you learned, maybe from the 1019 or 1090, the math course, discrete math. Okay? Now just mention the background very quickly. So when we got empty over here, it's really related to when we say all numbers positive, the OR over here is what people say, more formally, universal property. Okay, it's called universal property. We're basically asking, are all the members in a collection, in this case, the collection is the array, are all the members in the array satisfy certain property? It's called universal. Universal means everyone in the collection must satisfy this property. If there's at least one member that does not satisfy the property, then it should be false. I already gave out the hints, actually. All right? So let's now see. So this is a formal way to express this. This symbol here simply means for every. You may have seen that in your previous math course. Okay? We say for every x, and then every member of x must satisfy certain property. And the property right now is about x being positive, larger than 0. Right? That's the property. But we have a special case. The special case is the array here is empty. So that means x over here belongs to some empty collection, like empty array or empty set, just empty collection in general. All right? So it turns out this one here is always going to be equivalent to true. The brief reason is, since we cannot find any witness to prove that the property is violated, it's got to be true. All right? I'll write it down, and I'll try to guide you through again. It sounds a little bit weird at first, okay? So this one here, so there is no witness. Right, so I think when you do proofs in math, usually you want to find some witness to really prove, right? So this term may not be strange to you. There's no witness to show some violation. So in this case, I cannot find a number that's not positive in the empty array. In that case, all the numbers in the array must be positive. All right, so that's the reasoning, okay? On the other hand, just for the completeness of your knowledge, so we got universal property. But now let's say I change the question a little bit. I say rather than asking all the numbers in the array are positive, what about some or at least one number in the array is positive? Right? In that way, the empty array case will return a different result. Right? Now we completely change the problem to something called existential property. I'll write it down. Another one is called existential. Whether something exists. Existential property. All right, so that one there, formally, we'll use this like a mirror E. Patricia, let me finish this and I'll answer your question. Give me one moment. So this one here, you write the exist symbol, and then there exists X, and then at least one member in the collection that will satisfy the property. And the property here could be some number that's larger than 0. Over here. And then in this case, we have the special case where X is in some empty array or empty collection. So by definition, this is equivalent to false. Okay, let me write down the reasoning and I'll take your questions. Okay, so this way, how we judge is there's no witness for you to choose to make sure the property is satisfied. So it's got to be violated. Okay, so there is no witness to show some satisfaction. All right, once more, and I'll take question. For this one here, there is no witness that is not positive in the empty array. So that means everything in the empty array should be positive. This one here, there is no witness in the empty array to show me that there's at least one number that's positive. So that means it's just false. All right. Question. I'll pause a bit. This might be a little bit tricky. Let's clarify this. Question.
So for the first case, where
Yeah.
the array is empty, are you saying it is true because it's vacuously true, or is it?
Vacuously true. That's exactly the word. Yeah, that's logically what people would say. I would say usually, well, a little bit more logic. Once you get to more advanced, maybe coursing algorithm or even data structure, sometimes when you want to prove some property, if the property, we call it universe of disclosure, is simply empty, and you want to justify some universal property vacuously, it would just be true because you cannot find any violation. That's exactly right. Yeah. Good. Yeah, vacuously true or magically or trivially true. Okay. All right, anyway, so for this one here, for all numbers positive, it's going to return just true. All right. If I change the question to, is some number positive? In that way, it will correspond to the existential property. In that case, empty array should return false. All right, so think about that. It's very kind of, we're tying the programming to logic, really. Okay, that's good. And then for the rest of the test case, it's very straightforward. Let me talk about them quickly, and then we'll look at the Java code. So now this array here is not empty. Very straightforward now, right? So the only number there is 4. It is positive, so true. All right? So this will be true. And all the numbers here, 4, 7, 3, 9, all of them positive, so that'll be true. And the next array, you can see that we can find one witness of the violation. So false. It's not all positive. All right? So that would be false. So now the question is, how do we solve this problem here recursively? I think for the base cases, we pretty much already see, right? If the array is simply empty, we should really return true. That will be the base case we should have. On the other hand, what about if the array is somehow too big for me to handle right away? So I need to make some recursive call. So the way to solve this one is kind of similar to, I would say it's more like a combination of how we understand about palindrome and also the reverse of problem, right? We're kind of borrowing the idea from there. Okay? So it would be similar to the reverse of problem in the following way. We're going to split the string into the head and the tail. So this will be the head, the first element, and this one here will be the tail, the rest of the array. We're going to split it. Okay? And why is this also similar to the palindrome problem? Remember, for the palindrome problem, we look at the first and last character. If they are the same, we're going to look at the middle. If they are not the same, we don't even bother. Similarly here, we're going to look at just the head. If the head is already positive, that means we have a chance that the rest of the array are still all positive. On the other hand, if the first element, tentatively, let's say is -4, in that way, this is already not positive. So there's no way that all elements in the array are actually positive. So we're going to return false right away. Question? 0? Well, yeah, so since we say positive, right, it's going to be strictly larger than 0. So 0 larger than 0 would be false. You can, okay, so when we say, yeah, so positive over here means strictly larger than 0. So that means 0 is not positive. So 0 will be considered as a violation. Okay? All right, so let's take a look at this very quickly and see some idea. Let's say the method here is called all positive, all P. All right, and then I'm basically given A, okay, call by value. I'm given the reference to A. So think about A is right here, okay, the reference to this array. And then in the beginning, I want to go from index 0 to index 3. Okay, you can think about index 0 to index 3. So the whole array right here. Okay, so 0 and then 3. That's what I do. Okay, let me also highlight. So think about 0, 3. So 0, 3 right here. Okay, and then I'm going to split the array into first element, which is 4, and also the rest, the subarray, from index 1 to index 3. You can see this part here is from index 1 to index 3 to tell where the tail is. So that one there is going to be, okay, split into, okay, first of all, the first element, index 0, the head. A at index 0 should be larger than 0. And that one there, we know that 4 larger than 0 is true. And we're going to combine the result using the AND operator. So the short circuit evaluation is going to be very handy. Because the left-hand side is already true, we should bother to look at the right-hand side, which will be evaluating the recursive call. So that one there is going to be a recursive call, all positive. And that one there is going to look at this range of the indices from index 1 to index 3. So call by value, still the same A. And also go from index 1 to index 3. All right, so that will be just one unfolding, just one layer. Now we're going to trace one complete example. Here, I just want to show you quickly. Are we okay with this? Okay, good. I would say this will be a very common pattern you will actually see on the recursion on the array. But I think that when you try to coding that, the site I kind of recommended, and also the past lab, and also the tutorial I make available on the lecture site, you will see like a different flavor of the example. Yep, just explore it yourself. I think studying, spending a good amount of time on the recursion is also going to pay off for 2101 next term. All right. Okay, let's now look at the Java code. Okay, and then we'll do some tracing. So it's important to clarify the idea here because apparently there are two methods over here. Okay, and the first method here, all positive, right here. Okay, this one I didn't have space to declare. I didn't do that, but this one is meant to be a public method, public. Okay, which means everybody outside this class can actually call that method. Right, it's public. On the other hand, this method here, all positive helper, that one there is meant to be private. Only the current class can actually can access it. Right? We talked about public versus private before, right? The modifier. Okay. So this public method here, you can see the parameter is just the array. So for any user who actually want to use your implementation to find out if all the elements in the array are positive, they only need to give you the array. They don't need to give anything else. The user shouldn't really bother about giving you the indices about where to look at. They shouldn't. That's not their concern. All right? It's a design issue over here. So as far as the public perception is concerned, only give the array. Only just the minimum possible inputs to the user. And then this one here, the all positive helper over here, we use the array. And then we try to look at 0 to the last index, right? So 0 is always the first index. A.length minus 1 is always the last index. We want to look at the whole array. But we try to make a recursive method call. So this one here is a call to a recursive helper method. Let's also double check. Why is this helper method here recursive? You can see the all positive helper is calling itself right here. So that is the recursive call. So we just double check. That method there indeed is a recursive method. So here's a pattern. The public method is not recursive. In turn, that one there is going to call some private recursive helper method. And the recursive helper method typically will get the array, for sure the reference call by value. In addition, you should also get the range of indices to look at. So when you actually go through multiple number of recursive call, you're just going to change the indices around. But A doesn't change, call by value. Okay? All right, and then let's look at the base cases. So we got two base cases. So base case number 1, empty range, right? So when from is larger than 2, all right? And also when from is equal to 2, in that way, it will be exactly just one element. If there's only one element, just want to see if that's larger than 0. Right? So these are the two base cases. Of course, you can argue this here could be redundant, but I just kind of want to explicitly write it out. Just to say, if you only got one single element in the array, you should check whether it's positive or not. Okay, recursive case right here. Let's now try to visualize again what's happening here, and then we'll do tracing. So that one there, you can see we got array A right here. And then let's say array A is not empty, just make it a little bit easier for us to visualize. Okay? You can think about this one here when we first call 0 and A.length minus 1. So 0 and the last index here is A.length minus 1. Okay, so that one there is the blue range over here. That's how we start with. Okay, so think about that one there is what we start with. So now in order to actually process this array, it's too long for us to handle. So we're going to split it into two parts. Okay, so we're going to split it into, first of all, we got from over here. So from here is just going to be 0. Okay, you can think about the first call. This is going to be 0. You can think about this one here is A at index from. Is it larger than 0? If it is, then we look at the rest of the array. If it is not larger than 0, you can just return false. Okay, let's say it is. In that way, we're going to look at the rest of the array. So that'll be the from plus 1 and 2. Okay, so you can think about this part over here. This part, the tail. Okay, so this one here. Okay, so this will be, we want to say all positive, the same A. And then, so here you can think about this index here is exactly 1. So 0 plus 1. So that'll be from plus 1. And then 2. Okay, so that one there basically was saying we just look at this array instead. All right. When we trace one example thoroughly, you will see exactly how the from is going to keep adding, getting closer and closer to the 2 value. We'll do that, okay? But now just more like a conceptual. understanding. And of course, we're going to combine these two results together right here using %. This will be the kind of like a visualization you can maybe try to do, or even before you try to write out some Java code, just to sketch the idea to see how you want to split the input array and how you want to combine the result together. It can be handy, especially when you're just learning about recursion. Question so far? Okay. Let's now trace one example in detail. Okay. I got quite many examples here, so I would suggest I'll leave the simpler ones for you guys to do. I'll do the last one. Okay, that could be a little bit trickier to get right. Okay, let's do the last one. Okay, so there are some base cases for you to trace the code to see exactly which block of code is going to be executed and returned. And that one there is just going to eventually return true. Right? You can see all positive. I'll leave that also as exercise for you. But let's see this one here. This one's here. You can see that eventually we're going to return false. There's a negative number. But let's see exactly how that occurs. Let's do this one together. I kind of already draw the tree for the recursion already, just to save time. But I would say when you do the exercise, feel free to maybe grab a blank piece of paper and then try to do it from scratch. I think that'll be better for you to understand. Okay? Let's see. So for this one here, we start with the call right here. We call all positive. And then we try to call that on an array A. So array A is right here. Okay? So we're calling this. We start from here. In turn, it is going to make a recursive call. So let's say we call all positive helper right here. And we are passing just A, right? The same A, right? Callback value. And then we're given this interval from 0 to A.length minus 1. Let's do some calculation. So here you can see A.length is equal to 1, 2, 3, 4, right? You can see 1, 2, 3, 4 will be equal to 4, okay? So that means this one here will be 4 minus 1, which will be 3, okay? So that's why when you are calling this one here, is corresponding to, you call the all positive helper A and then 0, 3, 0, 3. Right? That's the first call. This one is not really like a recursive call just yet. Okay, so that one there is right here. Okay, so you can think about initially, we intend to look at the entire array, just the pink. Okay, right here. And let's now go step into the method call right here. So now we got 0 and 3. So for this base case over here, it's not going to be satisfied. 0 larger than 3, false, right? So bypassed. And then 0 equals 3, also false, bypass. All right? So we're going to go into this return recursive case. All right? So that one there is actually going to split into two things. It's going to split into A at index from, which will be index 0, which is what you will see right here. And A at index 0 is actually 5. So 5 larger than 0 is true. And since we're combining them using the AND operator, so we should really go ahead and evaluate the right-hand side, which is right here. All right? So that'll be the first recursive call, the first one. So this will be the first recursive call right there. Okay? So that one there, we are going to look at all positive helper and especially from plus 1 and then 2. Okay? How do we calculate that? From right now is 0. Plus 1 is going to be 1. 2 is 3. Remain the same. All right? So it can be 1 and 3. It's going to be 1 and 3. Okay? So you can think about for the first recursive call, we are looking at 1 through 3. Okay? Strictly smaller range. That's what we're doing. Okay? So that's right here. All right? So far, so good. And let's now make this first recursive call and see what happens. So what we do is we go step into the same method right here. Okay, right here. So now it's going to be 1 and 3, right? 1 and 3. You can double check here. The base case, 1 larger than 3, false, bypass. Base case number 1. And also here, 1 equals 3, false. You also bypass, right? And then you go for this recursive case right here. So let's see what's going to happen, right? So that one there, we're going to, let's say here. We're going to, first of all, go for A at index from. From index is 1. Okay, so that's why you see right here, A1, larger than 0. Okay, if you evaluate this one here, index 1 is 3. So we're basically evaluating 3 larger than 0. 3 larger than 0, which we know is true. And we have the AND operator right here. So because the left-hand side is now true, so we're going to go for the right-hand side. And for the right-hand side, it's going to be from plus 1. Okay, it's the orange part. Right? It's going to be from plus 1. The from right now is 1. 1 plus 1 is going to be 2. And then 3 remain the same. Okay, so it's going to be 2 and 3. That's why you see right here. Okay, so 2 and 3. All right, so far so good? Okay. You just need to be very clear about which recursive call you're tracing and how exactly the from and to values are being passed. That's really something you want to be careful. Okay. So after this one here, one more recursive call, right? So we'll try to just do one more. And let's now use the orange. So think about this one here is the second recursive call. Okay, second recursive call. All right, so calling this method again, but now it's going to be 2 and 3. So the value is going to be, I'll put it here, 2 and 3. Okay, so we start with 0 and 3, and then go to 1 and 3, and then we'll now go for 2 and 3. All right, if that's 2 and 3, and then this base case, 2 larger than 3, false. 2 larger than 3, false, bypass. And right here, 2 equals 3, also false. All right, and we go for the recursive case right here. All right, so that one there. Let's now use, how about, let's say, purple. Okay, so we're going to do, so the from is now 2. So what we do is, you can see A at index 2, right? You can see the from is now 2. So A at index 2 is minus 2. So this will be minus 2 larger than 0. All right, so now it's going to be false. Okay, be careful here. Let's see exactly. So this is the case where you don't have to evaluate any further. And the array has not been processed just yet. We don't have to go any further. Because now minus 2 is the first discovered number that's not positive. It's the witness of violation. Okay? Because we tried the short circuit evaluation right here. So now because this is false, short circuit evaluation bypass the right-hand side. Okay? So this part here is never evaluated. Never, ever. Right? It's very important to see. This one here, okay? So you can think about, for this particular n%, just for this part over here, right? Because the left-hand side is already false. Overall, it's going to be false. Because this is false, so that means the all positive, this one here, recursive call, is going to be false. All right? Because that will return false. If you try to combine the true here and false, it's also going to be false. So this part here will be true and false. It's also going to be false. So that means this recursive call is going to return false. Right? And then you look at true and false, this part here. This one here, true and false, of course, it's going to be false. So that means this one here is going to be false. And because that one's false, this one here is also false. That's the final result. You can think about once the result is somehow evaluated at the bottom level, it's going to be propagated somehow and evaluated. All right, any questions about this tracing here? So what's really important when you do this kind of tracing is you have to know, number one, about the call by value. We are not creating any new array object. We're passing the reference to the same array. Number two, you have to be very careful about how the indices of from and to are being passed. We start with the beginning and the end. That's typically the case. Not necessarily always, but typically that's the case. And then for every recursive call, you have to narrow down about the range of the indices, right? Oh, there's something I can also add. So the orange part is really about 2 and 3. So it should be right here, okay? So that's the final bit, okay? All right, if no questions, I think I want to talk about some background for the second example. The tracing will be very similar. I'm going to leave that to you. But I can talk about the idea for the second recursion problem. Okay. All right. No questions? Good. Okay. So the next one here will be about slide number, I believe 23. There we go. Okay, that's the last example. Okay. This one here, I'll just talk about the idea, clarify some terminology, and then the tracing will be up to you. Okay. So let's say we're still given an array of integers, and we're asking whether or not the array is sorted in a non-descending order. What does non-descending really mean? Not exactly. You're almost right. Yeah? Random, not maybe ascending or equal to. Maybe that's what you meant to say, not random. Yeah, well, if random, there's no way it's sorted, right? Okay, let's clarify this. So this is a very typical way people will refer to the sorting order. So there are 4 possibilities. People might say ascending, descending, non-ascending, and also non-descending. So these are the 4 possibilities. Let's clarify exactly what they meant. And then we'll talk about how to solve this problem very quickly. All right. So let's talk about here. Okay, there are 4 possibilities right here. Okay, let's talk about them. Let's talk about the descending and also ascending. These are very straightforward. There's no ambiguity there. Well, none of them got ambiguity, but it's nothing tricky. Okay, and for descending, you can also say decreasing. For ascending, you can also say increasing. Okay, that's also understandable. Okay. For decreasing, that simply means when you actually go from left to right, the value should go strictly downhill like this. For increasing or ascending, when you go from left to right in the array, the element should really go strictly up for the trend, right? That's visually. But let's see some example. So to start with, let's say for descending, 5, 4, 3, 2, 1, right? If you look at any adjacent 2 elements, right? In that case, you can see that the left element should be strictly larger than the right elements. Okay, so the trend will go like this. If you pick any element at index I, its neighbor to the right, A at index I plus 1, you should really get larger than. That's why you're going downhill. Okay. Ascending, increasing will be exactly the opposite. So example would be 1, 2, 3, 4, and 5. Okay. So let's say we got 2 and 3 over here. So here, if you look at the left element, should be strictly smaller than the right neighbor, right here. So the value, the plot, will be exactly the opposite, symmetric. So if you pick element at index I and compare that with its neighbor to the right, I plus 1. So that should be strictly less. Okay? Strictly less. Okay, so these 2 must be very straightforward, nothing tricky. Okay? What about non-descending, also non-ascending? Okay? So let's talk about it. Let me pick maybe non-ascending as an example. Okay? When I say non-descending, So this part here, none, really correspond to like a not, or more formally, negation. That's a negation symbol. You may have seen that in the math course, or if you like, in Java, it's the exclamation mark, right? Just a not a case. Not a case, descending. All right, let's now try to formulate that a little bit. So by definition, not a case, descending. Okay? And then descending, according to our definition, is right here, right? Descending. So that's equivalent to not a case, A at index I larger than A at index I plus 1, right? I'm copying exactly just here, right? It is not a case, descending. Yeah, exactly. So once you distribute the negation over the larger than, you will get it less than or equal to, right? Exactly, right? So what will be the not the case larger than? It should be less than or equal to, right? So that one there will be equivalent to A at index I less than or equal to A at index I plus 1. All right? So now you can think about this part over here is not random, but equal, right? Equal to, and this part over here is about ascending. So when I say non-descending, I simply means the elements may either stay the same or they might be ascending. Either way will be okay. So let's look at how do we plot it. So very straightforward. You can either go ascending or you can stay the same, and then you can go ascending again. Basically like that. You're climbing a stair, basically, right? On the other hand, if you say non-ascending, I'll let you work out the math analysis. It could be either you're climbing down or stay the same, or go down again, right? Exactly symmetric. So example, for non-descending, you may have 1, 2, 2, 3, 4. You can see this part over here is about equal. And this part over here is about ascending. Okay? And what about non-ascending? Let's say 4, 3, 2, 2, 1. So this part here is strictly descending. Right? 3 larger than 2, descending. And this part here, if I say 2, 2, this one here is not really change, right? All right, question over here. So just be sure to really understand about these 4 different scenarios. But for the example problem we're trying to solve now recursively is about non-descending. Okay? Yeah, non-descending. As long as it's not descending, we are okay. Right? Let's see. So now, how about this one here, empty array? You always got to deal with it. Can I say the empty array is sorted in the non-descending order? True or false? True? Okay. Similar arguments. You cannot find any pair of element that is not non-descending. That's basically the argument. You cannot find any witness of violation. Similar, okay, as before. Okay, and then over here, if I got 1, 2, 2, 3, 4, true, right? It's either equal or ascending. And also 1, 2, 2, 1, 3. How about this one here? Is that non-descending? True or false? False? Why? Give me a violation pair. To 1, right? Exactly, right? So once you get to here, you can that one and its neighbor, compare that, you're descending, right? Which is not right. All right, good. How do we solve this recursively? It would be very similar to how we did it for is like all positive, very similar. But now you just got to be careful about comparing some element with its right neighbor. That's really the tricky bit you want to get right. Okay, let's see. Okay, I'll talk about the idea very quickly and then we can move on. Okay. So for empty array is going to be, let's go for another 5 minutes or so, and then we can wrap up the course, and then we'll take a short break. Okay. So this one here is actually true because cannot find violation. And also this one here, like a one element array, by definition is also sorted because you don't really see the trend. You cannot find violation. All right, so this one here is true. But this one here, because you can see from 6 to 5, it is false. All right, so these are the 4 examples. You can definitely do the tracing by yourself. It's something very similar to what we just did for the all positive. I'll leave that to you. Okay? But let's talk about the idea very quickly. So let's say this one here. If I take this array, it got indices 0, 1, 2, and 3, right? 4 indices. Let's think about without a recursion. How exactly do I evaluate it without a recursion, without a loop? How do I write a single Boolean expression to evaluate it, right? It's going to be A at index 0 less than or equal to A at index 1. And A at index 1 less than or equal to A at index 2. And A at index 2 less than or equal to A at index 3. Right? Agree? So these are actually the ones you want to compare. Okay? You can think about the 0, 1, and 2 over here would be the from index. So the from index can start with 0 and then increment to 1 and increment to 2. Right? Because every time when you get the from index, you can always compare with its right. When you get to here, compare with its right. Here, and also compare with its right, etc. Okay? So that's something you will boil down into. But let's see how we can convert this into some recursive call. Okay, let's see. So let's say I start with the is sorted. Is sorted. Okay, I'm still taking this array, for example. I'll say A here, and then index 0, index 3, right here. All right, so that one there. So you can see I cover the entire array, index 0 to index 3. So what I do is I try to look at 0 and 1. Right, let's say. So I would just need to split it into 2 parts. A at index 0 less than or equal to A at index 1. And then ampersand, ampersand. And then I'm going to make a recursive call. Is sorted. And call by value A. So now the question is, what should I pass over here? That's a question. So how about the first one? Should I keep from? Yeah.
Which is next to index, I think plus 1.
Okay, I like it because, okay, so guys, okay, be careful here. That's why I want to pause a bit, because a little bit more slow. This number here, should I put from plus 1 or from plus 2? Plus 1. So think about here. This is what we're doing now. The next recursive call, I should really expect to compare 1 and also 2. So that means when you say from plus 1, it will be able to go from 0 to 1. So from plus 1 will be the case. But if you say from plus 2, you're now jumping the index for too far. All right, so that's why I kind of give you this just to look at first. Okay. So that will be the trickiest one. So once you get from plus 1 over here, that's good. And then you're going to say 2. All right. So try to really link the from plus 1 here with the 0 to 1. Okay, I think that can remind you about the reasoning. All right. All right, so that's the recursive thinking, right? We just split the array, again, from the head and also the tail. And if you look at the Java code very quickly, just 1 minute, and then we can wrap up the course. We got a public method here, which will take just the array. And we call the recursive helper method right here. And this one here will take the from and to, right? You can see we got base case, number 1, base case number 2. And this one here, you look at from and from plus 1 to compare them first. And then you got to say from plus 1 to move to the next index for the recursive call. Okay. So very much corresponding to what we just talked about, right? So now your job to really complete studying this example will be try to trace, ideally all of them, about these cases. The base case, empty array, and also array of 1 elements. And this one is supposed to return true. And this one here is supposed to return false, right? Choose at least 2 of them to really try to trace and make sure you feel comfortable, all right? All right, question? All right, so now you have seen basically recursion on numbers like Fibonacci factorial, recursion on strings, palindrome, reverse, occurrences of, also recursion on the array is sorted or positive, right? You have seen many examples already. And also with all the study resources on the lecture site, you got enough to really go over, right? If no question, let me spend about 1 minute or 2 just to wrap up the course, and we'll take a short break, and I'll talk about the exam. All right, I think that's important for you guys as well. Okay, let's now take 1 minute or 2 just to wrap up the course. Question? Yeah, go ahead.
That second argument that is taken as an index, what index is that?
Sorry, you're talking about iPad notes, right? Are you talking about the slides over here or the notes over here? This one here. Okay, which one are you talking about? The second argument, you meant the, this one? Or this one? You mean this one here?
Yeah, from the 2, it's like from specific index to certain.
Exactly. So you can think about this pattern here. You're trying to use the from and to, the 2 integers, to form a range of the indices you want to look at for the array. And for every recursive call, rather than creating subarray, you want to create sub-ranges, right? All right, good. Good, all right. So let's now look at course wrap-up. Okay. All right, this is not really like an exhaustive list, but at least some important topics that we cover in this course. So this can be also potentially a reference guide for you to go over the topics that we have covered in this course when you study for the exam. So procedural programming, exception, of course, you talk about exception objects, but I'm more putting that in the context of chain of method call. That's really what I meant by procedural programming, not too much object orientation. Okay? Exceptions, we learned about it, call stack, and also the catch or specify requirements, and recursion for sure. I would say, arguably, this topic now would be something you definitely want to spend more time, so that will pay off when you get to the 2101 in the winter. Right? So I think for 2101, of course, it also depends on your professor. They might emphasize maybe a little bit more on the programming. They might emphasize more on the theory, but I think either way, you have to know recursion well. I think this is just going to be the next level of knowledge you have to grasp in 2101. Okay? So I think definitely spend more time, as much time as you can, about recursion before the exam. Okay? Especially about recursive thinking, implementation, and also tracing, especially using a recursion tree to see how you can think recursively. That will be the most important learning outcome. Right, data structure, we don't really talk about many data structures, it's only one, just array. But we definitely somehow master the very basic, like indexing, using a for loop, or even nested for loop to really manipulate the array. But in 2101, the follow-up course, you'll learn about something called linked list. It's more like a competitor to array to see which one might be more efficient. That's something we'll study more thoroughly. And also, the arrays and linked lists are something we call linear data structure. We'll also learn about non-linear data structure, which is like a tree, right? You'll learn about tree. Have you learned it before? You have, okay. What tree did you learn? You even learned about heap. Okay, good for you. Okay. Anyway, so your fellow student, what they just mentioned about heap is also something you're gonna learn as well. Also gonna, Sorry. Wow, good for you. Good for you. Okay. And also in 21, we're also gonna learn about sorting and searching, right? So we don't really talk about sorting. For example, given an array of random numbers, how do you sort them in the non-ascending order, for example, right? You learn about different sorting algorithms. Okay. Okay, that's to come. Not for this course, but something you can look forward to. All right, and also OOP in Java. So yeah, so basic OOP methods, dot notation, aliasing, inheritance. We spend a lot of time on the inheritance. So if you kind of ask me, should I study a lot about inheritance? It sounds like a good idea to me. You definitely want to go through recursion a lot for the exam, for sure. Okay, no doubts. And also pay attention to the design principle, like a single choice principle, cohesion, right? So these are good stuff for you to keep in mind. Okay. Polymorphic array, that's really the final outcome that we had, right, from the inheritance. Okay, and class cast exception, and also instance of, right? All right, also Eclipse. Eclipse is just one example IDE. So I think whatever debugging breakpoint scale you pick up from Eclipse, you can apply that to any other IDE, like IntelliJ, Visual Studio. They all support the same features, right? I think I definitely haven't really wasted your time. All right, so this is the only topic I think it'd be worth. Generics is not covered in the exam. However, for those of you who may want to dive a little bit further from inheritance, generics is just another natural extension to inheritance. That's something you may want to maybe spend some time, right? Optional for those of you who might be more desire to learn a little bit more during the break, but optional. All right, so my suggestion would be, so there are two possible things you can do, maybe beyond this course. So one would be you want to sharpen more about your Java skill and unit testing skill. Question first.
Sorry, you mentioned the generics wasn't on the exam.
It's not on the exam.
Does that include abstract classes and
So abstract classes, interfaces, they will be on the exam. Because those are the required background study for Lab 5. Yeah, good. So the first suggestion here is, this is a very classic textbook for EECS2030G. Maybe in your third year, not yet, but this is a very nice book to really have a sharp list of all the well-known common algorithm. The good thing is they specify the algorithm in the pseudocode, not Java, not C, not Python, in a way that you can get an idea computationally. So once you see the pseudocode, understand the mathematical analysis, you may just want to implement that in Java or any programming language you like. Can be Python, can be C++, can be JavaScript you like, or Java, right? And then once you implement the algorithm yourself, try to write some JUnit test cases. It's very good. It's going to be very solid exercise you can do, but it's not going to be like overnight exercise. This will take a lot of time, right? So plan your time if you're willing to invest yourself some practice. This is one thing. Another thing, since we learned about inheritance, another very good way to really go deeper about inheritance is there's something called design patterns. So this is more like a topic in 3311, software design. So design patterns are basically different scenarios that industry identify as problematic scenarios. And for each problematic scenario, they have some particular solution for that. And this is a very classic textbook on design patterns. I think that the language there is like a C++. Have you seen that book before? Yeah, anyway, so yeah, that one is not exactly Java, but since you learn about OOP and inheritance, this book is right at the right level for you. And guess what? Your lab number 4, I was actually using one of the patterns without telling you. It's something called the observer pattern we did for lab number 4. You kind of just did it without knowing it's observer. The name is not important. The most important thing is you know how to do it. Okay? Anyway, so this design pattern book here has many good patterns there for you to explore. So many. Right? Again, similar exercise, understand the concept and translate into Java and write some JUnit test cases. Right? You just need to keep practicing, right, for your programming. I think the bottom line, in any curriculum you might study in the university, they will never give you enough chance to really practice programming. If you only rely on the class, in-class example, the labs or assignments for practicing your programming, never sufficient. You will have to spend some extra time. That'll be my honest advice. Okay. All right, final slide, and then we'll take a short break. So whatever you learn in this course will be assumed in 2101 next term, especially if you are going to take it with me again. I'll be teaching the engineering section again. Then definitely I'll assume you kind of know well about Java. And also, we also need to dive deeper into some math, especially how to justify some data structure, etc. So whatever you learn in 1019 or 1090, either way, like a big O notation, for example, there will be something you may want to learn, may want to review, brush up. All right, so Java will still be assumed in 21, so don't abandon that. You really want to keep practicing. All right, that'll be it. So why don't we take a short break, and then we'll talk about the exam, okay? All right, so for the recursion lecture, so there's one example that I'm not able to really cover that in class fully. This on the slides is called the Tower of Hanoi. You may have seen that example maybe in your previous math course, but now we can actually let you solve it in Java, right? So I already put down the resources for studying this example here. This one here is required, and you may be covered in the exam. Okay, so you can go over the slides, but if you want to look at maybe some recording, you can also do that. Okay, I'll show you where to find it. So just go to the lecture site, and then you will see that right here, right? Required readings over here, Tower of Hanoi, right? You got all the resources there. You got notes, you got the Java code, also you got the recording over there. All right, just make sure you also plan to study that as well for the exam. Okay, so let's now talk about the exam.